The purpose of this video is to revisit the work on ionization energies, and particularly take it further by looking at how successive ionization energies can be used to predict the number of electrons an atom has in its outermost energy level, and hence work out the group number of the atom. Your first task is to check, do you know the definition of first ionization energy? So on a piece of paper, quickly jot down what you think the definition of first ionization energy is. I'm going to pause the video so you can do that now. Okay, so look at the definition that you've just written. This is the kind of thing that comes up in an exam quite frequently, and it's usually worth 2 marks, sometimes 3, but usually at least 2. There are certain things that clearly you have to say. First ionization energy is the energy required to remove 1 electron from each atom. You're going to get a mark for saying that. In 1 mole of gaseous atoms. That would also be worth 1 mark, possibly 2, if the examiner was feeling particularly generous. So it's about removing 1 electron from each atom in 1 mole of gaseous atoms. That's a definition you absolutely have to learn, and it's really, really worthwhile making a flashcard, revisiting that definition and checking that you know it. Keep doing that throughout the course. It's that spaced repetition of learning that's going to help you memorize things. Now we can see, written down here, we've got an equation, which you should already be familiar with, about how to write first ionization energies. We need to start with the element as an atom in its gaseous state. So here, for example, we've got Na as a gas. And what's happening is the sodium atom is going to lose an electron to form the sodium ion. Now, because we're writing this as an equation, the equation is telling us that we're doing this for 1 mole of sodium atoms to form 1 mole of sodium 1+ ions and 1 mole of electrons. That's first ionization energy. Now, of course, it's possible to take any atom and remove more than 1 electron. That's obvious for things in group 2 or in group 3, because you know that they form +2 or +3 ions. But we can actually take off as many electrons as an atom has. Clearly, it's going to take a lot of energy to do that. But what we can do is write an equation to show each electron being taken off in turn. We've already just looked at and reminded ourselves about the equations for first ionization energy. So what you need to do here is have a go at writing out second, fourth or third ionization energies, as the question asks. Look at the definition and look at what it explains second ionization energy to be. It's telling us it's the energy required to remove 1 electron from each 1+ ion in 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions. So think about, when writing the equation, what are you going to start with and what will you finish with? So pause the video and have a go at the first one of these, and then we'll rejoin the video in a moment to check whether you have it correct or not. Hopefully you can see, here is the second ionization energy of sodium. We're starting with the sodium 1+ ion in its gaseous state. Everything always has to be a gas, so we always need to put our state symbols on, and it's always going to be a G for ionization energies, irrespective of what type of element we start with. And we're going to form in this equation the sodium 2+ ion. So in the second ionization energy, we're forming the sodium 2+ ion. If I were going to be doing, for example, the 8th ionization energy of an element, I would be forming the 8+ ion. And I always form it from the ion which has a charge of 1 unit less. So again, in one moment, I'm going to pause the video to allow you to have a go at completing the remaining questions that you can see currently on the screen. So on your pen, with your pen and paper, have a go at those and just check whether you have got them correct. So here we are. Second ionization energy of lithium, again, in just the same way as we did for the first one, we're going to start with the lithium 1+ ion and turn it into the lithium 2+ ion, everything in its gaseous state, plus a mole of electrons. For the fourth ionization energy of copper, we need to form the copper 4+ ion, again in its gaseous state. So we need to start with the copper 3+ ion. Every single one of these equations, irrespective of which ionization energy we are doing, we are only ever removing 1 mole of electrons. So finally, the third ionization energy of nitrogen, the N2+ ion, is going to go to the N3+ ion. Now I know in the real world, in terms of nitrogen, in terms of how it reacts in chemical reactions, you'd expect nitrogen potentially to be forming a minus ion. We're not doing that here. We're looking at ionization energies. And ionization energies are always about the removal of electrons. How much energy does it take to remove a certain electron? The first, the second, the third, however many. This last question, how many ionization energies are possible for boron? It's not a trick question. What you've got to think about is, how many electrons does boron have? Obviously, you'd look at a periodic table, you'd find boron, you'd look at the atomic number, and that would tell you the number of protons. And we know that the number of protons and the number of electrons must be the same for an atom. So boron, atomic number 5, has 5 protons, 5 electrons. If the electrons we're interested in for ionization energies, it's got 5 electrons, so we could potentially remove all 5 electrons. So boron would have 5 different ionization energies. And to remove the first, and to remove the second, and so on, all the way up to the 5th electron. Okay, put your study pack to one side. What we need to think about now is how much energy does it require to remove each electron from an atom? Bit of a crazy graph here. It's a bit made up, but it's a way of getting you to think about the issues at stake. On the y-axis, we're thinking about how much energy do you need to put in to pull off an electron. And on the x-axis, we're talking about which electron are we trying to pull off. Let's use carbon as an example. So first of all, think about what is the electronic configuration of carbon. Carbon's got an atomic number of 6. So clearly we'll start with 1s2, 2s2, 2p2, 6 electrons. Now when we take electrons off, we're clearly going to take electrons off from the outermost energy level. The outside electrons come off first. They're the ones which are highest in energy. That's what you've been taught. They are the ones which are furthest from the nucleus. That's what you have been taught. They're the ones which are easiest to remove. So if we think about this graph, how much energy is needed to pull off the electron? Clearly, pulling off the first one is going to be the easiest thing to do. So I could start down there. I've got to put some energy in, but it's clearly going to be less than the next electron that I need to remove. So what I want you to think about, again, we're going to pause the video in a moment. What I want you to think about is, what shape will this graph have? Okay, so we'll pause the video now. You'd think, what will the shape of this graph be? Sketch it out, and then we'll come back in a moment and see if you're right. So pause the video now. Okay, it's possible that you might have drawn a graph that looks like this. What you're showing if you've got a graph that looks something like this, is it gets harder to pull off each electron in turn. So the first one's the easiest to pull off, and then the second one it's harder to pull off, and then it's harder to pull off the third, and so on and so on and so on. So that's one possibility. You may have thought about it like this, that you've seen, for example, we've got 4 electrons in the second energy level and 2 in the first energy level. The 4 in the second energy level are further away from the nucleus, and the 2 in the first energy level are closer to the nucleus, so you may have drawn something that looks like that, showing that the energy required to take off the first, second, third and fourth is similar, and then the energy required to take off the last 2 is more, and that there's some kind of step in the graph. Don't worry about where the graph actually starts. I'm just separating them out to make them easier to see. Some of you, or you might have thought, well, okay, we've got 2 electrons in a 2p subshell, so they're easy to take off, and then we're going to have a step up to the third and the fourth, and then a step up to the fifth and the sixth. So we have 3 options. Surely they can't all be right. They're all saying something slightly different. The blue line is telling us that it just gets more and more difficult to remove electrons every time you take one off. The red line is showing us that there's a stepped process, that the 2 electrons in the 2p subshell are easier to remove than the electrons, the third and the fourth electron, which are in the 2s subshell, and the fifth and sixth electrons are the hardest ones to remove because they're in the 1s subshell, or the first energy level. The green line is telling us that the first 4 electrons corresponding to the ones which are in 2p and 2s are easy to remove. They're all in the second energy level, but then it becomes much more difficult to remove the electrons which are in the 1s subshell, or the first energy level. That would be the fifth and the sixth electrons. So which is right? So think about what you've drawn. I'm going to again pause the video for a moment and allow you to think about which of these makes the most sense. It might help to think about a diagram like this. Diagrams like this you should be pretty familiar with. We're showing the energy levels, we're showing the suborbitals, sorry, the subshells, and then the orbitals within each shell. So we know that carbon, for example, has 2 electrons in the first energy level. It's got 2 electrons in the 2s subshell, and it's got 2 electrons in orbitals in the 2p subshell. To make sure we use words like orbital, subshell, and shell correctly. Orbital, remember, is a place that can hold 2 electrons in space. Our energy levels are made up of subshells, S subshells and P subshells. Now, looking at this diagram that we've just drawn, we should be able to see that there is a big jump between the first and the second energy level in terms of energy, and that there's a small jump between the S and the P. So we're looking for a big jump between the S, 1s and the 2s, and a very, very, very small jump in comparison, very small in comparison between the 2s and the 2p. So how will that affect the graph that we've just drawn? Well, it will mean that these electrons are much easier to remove than these 2, the 1s ones. So that would suggest that perhaps the green line is the correct one. 4 electrons are going to be a lot easier to remove than the innermost 2 electrons. Now, it is possible that you might see a little step between taking off these two compared to these two. The 2 in the 2p compared to the one that was in the 2s. But that jump is so small that we're not particularly going to appreciate that step. But we are going to see a big jump between the second energy level electrons and the first. So the green line is looking pretty promising. I haven't rubbed the blue line out. So there's something about the blue line that I do like. The blue line is showing that as you remove each electron in turn, it becomes harder to remove the ones which remain. And that kind of makes sense. If you think about trying to remove an electron from an atom, that's clearly going to take energy. But when you do that, you form a 1+ ion. So trying to then pull an electron off that 1+ ion, trying to remove a negative electron from a 1+ ion is going to be more difficult. Similarly, if you try to remove the third electron, you're going to be pulling that off a 2+ ion. So again, that's going to be even more difficult. So something has been communicated with the blue line, which is telling us that it gets more and more difficult to remove each electron in turn. So somehow we need to take account of the blue line when we draw the green line. What I've tried to do here is amalgamate those two ideas. Hopefully you can see that the red line continually goes upwards. It's telling us that it's becoming more and more difficult to remove each electron in turn. But we've also got a step, a big jump, a really big jump between the 4th and the 5th ionization energies, or the 4th and 5th electrons being removed. And that would correspond, if we think about it, the first 4, as we've said, the ones in the second energy level are easy to remove. So these come from the second energy level, whereas the 5th and the 6th are coming from the first energy level, much closer to the nucleus, much more tightly held. I'm going to bring this video to a close, and what we're going to do in the next video is look at the remainder of the study pack to do with ionization energies. And you're going to be predicting what graphs like this will look like for specific elements. So you'll need the study pack, print that out if you need to, and we'll be going through it.